Namaskar friends. Welcome to the educational video lecture series by MedDwise Circle. This video lecture series is made in collaboration with Anamol Laboratories Private Limited. In this video lecture series, we are discussing the fundamentals of clinical chemistry test which are performed in pathology laboratory. So without wasting any time, let us go back to our slides and start the video lecture series. Please allow me to share my screen. Friends, I hope my screen is visible to everyone. As I told you, in this video lecture series, we are discussing about the fundamentals of clinical chemistry test in every pathology laboratory. This entire video lecture series is divided into multiple modules. In the first module, we discussed what are the basics of photometry, in which we discussed what is wavelength, what are complementary colors, what is Beer-Lambert's law, and how Beer-Lambert's law is implemented in pathology laboratory, what are the components of colorimeter, and what is the difference between colorimeter and spectrophotometer. All these videos are available in our previous videos. In this particular module, we are discussing how enzymes are important in diagnostic test. In our previous video, we discussed what is the role of enzyme in diagnostic test and how this is important to us in our day-to-day pathology life. In today's video, we are going to discuss what are the factors that affect the enzyme activity. So before we understand what are the factors that affect enzyme activity, let us quickly recap what is the role of enzyme in diagnostic test. Friends, we understood in our previous video that enzymes are proteins that are nothing but catalyst to increase the speed of the reaction. In our human body, there are multiple biochemical reactions that takes place continuously. Enzymes simply increase the speed of the reaction. How they do it is by enzymes first form a bond with something called as a substrate, and then it forms an enzyme substrate complex. Then this is the stage where the substrate is converted into product, and then the enzyme releases the product back into the system. Friends, it is important to note that just like any other catalyst, here even the enzyme quantity does not increase or decrease. Only the speed of the enzyme increases or decreases. This is important to understand because for some diseases, the concentration of analyte either increase or decrease. That is why the disease happens. For example, in diabetes, the concentration of glucose increase or decrease. But there are many diseases in human body where enzyme concentration does not increase or decrease. Here, the activity of enzyme either increases or decreases. Because since enzymes are catalyst, they do not take part in the reaction. Therefore, their concentration remains constant. We also understood that enzyme activity is important to measure. There are several attributes of enzyme activity. The first attribute is that enzymes are very specific to one particular substrate. For example, glucose oxidase enzyme only acts on glucose molecule and it does not act on any other sugar. This is the reason why even enzymes are added in the diagnostic reagent and they are provided in the form of kits. We also see that the reaction happens because there is a minimum amount of energy required for the reaction to happen, which is called as activation energy. Enzyme simply reduces the activation energy. That means even if the system has low energy, still the reaction can be initiated. We have also seen that enzyme activity can be measured. It can be measured in two ways. Either enzyme activity can be measured by amount of substrate consumed in the reaction per minute or amount of product formed from the reaction per minute. We have also seen that enzyme activity depends on certain environmental factors. Let's try to understand what are the environmental factors that affect the enzyme activity. Friends, enzyme activity is also termed as enzyme kinetics. We have seen that there are five major factors that affect the enzyme kinetics or enzyme activity. The first one is pH. If the pH of the reaction mixture changes, then the enzyme activity is affected. Either it is increased or decreased. We also saw that ionic strength of the buffer is very important. If there is a weak buffer or a strong buffer, it affects the activity of enzyme. We also saw how reagent to sample ratio was important. When the reagent to sample ratio was changed, how it affected the enzyme activity. We also saw how measuring the enzyme activity in the right time of the reaction was important. If we measure the enzyme activity in lag phase, we will get wrong results. And if we measure the enzyme activity in log phase, we will get the right results. We also saw how temperature was important and why flow cell temperature is very critical in having good enzyme activity. Now, with this brief introduction, we will go to our next topic, which are what are the different types of biochemical reactions that happen in every pathology laboratory. Friends, there are basically three major type of biochemical reactions that happen in pathology laboratory in clinical chemistry. The first type is called as endpoint reaction. The second type is called as kinetic reaction. Sometimes it is also referred to as rate kinetic reaction. Few people also call it as rate reaction. The third type of biochemical reaction is fixed time, or it is also called as 2 point. This is one of the type of kinetic reaction only. So what exactly is endpoint reaction? We will try to understand each one of them in detail. Let's start with our first thing. What is endpoint reaction? Friends, we all know that in every pathology lab, when there is a reagent which is added in the test tube and the sample is added in the same test tube, the reaction happens. Now, what is the point where we have to take the absorbance? Do we wait for the reaction to complete and then take the absorbance? Or do we take the absorbance while the reaction is still in progress? In case of endpoint reaction, we wait for the reaction to first get completed, then take the absorbance. Why this is like this? Because let's take an example. We want to estimate how much glucose is present in the serum. Now we have to allow the reaction to first get completed. In the test tube, there is a reagent in which there are certain enzymes. And then we add patient sample into the same test tube. When we add patient sample, this is the point where the reaction starts taking place. When the reaction starts, we have to allow first the reaction to get completed because all the glucose molecules which are present in the serum, they need to be converted into the final product. Here, the final product is colored in nature. And then we add this final product into the analyzer and we measure the absorbance of the colored solution. Now, say for example, if the reaction is not complete, what will happen? The color formation is incomplete. When the color formation is incomplete, that is the time when we measure the absorbance, we will get low OD. When we get low OD, ultimately the instrument using Beer-Lambert's law will calculate the concentration and eventually we will get lower concentration. And we will falsely think that actually the patient is suffering from the disease. But on the contrary, the patient is perfectly healthy. We have not allowed the reaction to get completed. So endpoint reaction means the point at which we are taking the absorbance. That point is only done after the reaction is complete or at the end of the reaction. If you can see this particular graph, on left x-axis, we have plotted the time, and on the y-axis, we have plotted the absorbance. So 0 point is the point when in the reagent the sample is added and the reaction is initiated. Or when the reaction is initiated, obviously the color formation is initiated. So here at this particular point, we will see that there is no further development of the color because now the absorbance is not increasing proportionately when the time is increasing. So this is the point where whatever the color was supposed to be developed, that particular color has been developed. In simple language, all the glucose available in the serum is converted into the color. So we take the absorbance only at this particular point. This is why this particular type of reaction is called as endpoint reaction. How the instrument calculates the concentration? The instrument calculates the concentration of glucose by using Beer-Lambert's law, which we discussed in our one of the previous video lectures. In Beer-Lambert's law, the formula of factor is concentration of standard divided by absorbance of standard. So what the instrument actually does is, first it will take the absorbance of the standard and then it will calculate the factor by dividing the concentration of standard divided by its absorbance. Using this factor, when we aspirate the patient sample, which is our second tube, then the instrument will simply multiply the absorbance of that particular sample with the factor. This way, the instrument calculates the concentration of glucose. This type of reaction, which is endpoint reaction, is very frequently used for those analytes whose concentration increases or decreases whenever there is a disease. For example, for estimation of glucose or cholesterol or estimation of triglyceride or albumin or total protein, etc. Each of these analytes will cause a disease because their concentration increases or decreases in the blood. Therefore, we use this method of endpoint calculation of the reaction. Now, friends, let us go back to our previous video lecture. In the previous video lecture, we understood what are enzymes. We also understood that enzymes do not take part in the reaction. Therefore, the concentration of enzyme before the reaction and after the reaction is the same. Hence, if we have to estimate whether the patient is suffering from any disease or not, then we cannot estimate the concentration of enzyme. Here we have to estimate the activity of enzyme. So whenever we have to estimate the activity of enzyme, shall we wait for the reaction to get completed? The answer is no. Because if we wait for the reaction to get completed, after the reaction is complete, the enzyme activity will not be seen. Therefore, enzyme will show as low as zero activity originally before the reaction. So endpoint reaction, we cannot wait for the reaction to get completed. Here we have to take the absorbance as and when the reaction is still progressing. Now, we have already discussed in our previous video that enzyme activity can be estimated by two ways. Either we can measure the amount of substrate getting consumed per minute, or we can estimate the amount of product being formed per minute. If we measure the amount of substrate being consumed per minute, then originally we will have very high absorbance. As and when, because the concentration of substrate is very high, as and when the substrate is getting consumed into the reaction, then the absorbance will keep on decreasing, as which is visible in the first graph. When we plot time on x-axis and absorbance on y-axis, we will see that in decreasing kinetics, when the time is passing on, the absorbance is slightly getting reduced. This type of reaction is also called as decreasing rate kinetic. Here, the initial absorbance is very high, and the final absorbance, which is our measuring point number 2, is lower from the initial absorbance. Friends, there is also one more important difference. In the endpoint reaction, we only take one absorbance after the reaction is completed. But in kinetic reaction, we have to take minimum two absorbance. One absorbance at the start of the reaction and one absorbance at the middle of the reaction. Because here we are calculating the difference in the absorbance. That is how we will find out the enzyme activity. So in a decreasing rate kinetic reaction, we will take measuring point number 1, which is our OD number 1, and we will take OD number 2. Both of these ODs have to be in the log phase of our reaction. We cannot take the measuring points in the lag phase of the reaction. Therefore, this particular reaction is measured only in the read time. They are not measured in delay time. Naturally, OD number 1 will be more than OD number 2 because the substrate present in while measuring the first OD was higher and the substrate present on while measuring the second OD was slightly lower. On the contrary to this, if we are not measuring the substrate consumed per minute, then we are measuring the product formed per minute. When we measure the product formed per minute, naturally, the first OD or the first absorbance will be lower and the second absorbance will be higher than the first absorbance. The reason being, if we plot the graph of time on x-axis and absorbance on y-axis, during the initial phase, during the initial time of the read time, the amount of product formed will be low. But when the reaction progresses, the amount of product formed will be high. Therefore, OD number 2 will be higher than OD number 1. Sorry. This is the difference between decreasing kinetic rate reaction or increasing kinetic rate reaction. Certain examples of decreasing kinetic rate reaction are SGPT, SGOT, LDH. These activities are measured in decreasing kinetics. And certain examples of increasing kinetic reactions are CKMB, CKNAC, gamma GT, alkaline phosphatase. These enzyme activities are measured by estimating the amount of product formed per minute. Therefore, they follow the second reaction of increasing rate kinetic. Now, friends, what is the meaning of, how do we calculate the enzyme activity? Friends, again, Beer-Lambert's law is used. Now, in case of endpoint reaction, factor was calculated by concentration of the standard or the known value divided by the absorbance of known value. Now, that was possible because we only took one absorbance. But in kinetic one absorbance. So known value sample is divided by delta absorbance of known value. What exactly is delta absorbance? Delta absorbance means the change in absorbance per minute. If the first absorbance is higher, sorry, in case of decreasing kinetic, if the first absorbance is higher and the second absorbance is lower, the formula to calculate delta absorbance is OD number 2 minus OD number 1. In case of decreasing kinetic, OD number 2 is low and OD number 1 is high. Therefore, delta absorbance will be negative. But we have to ignore the negative sign. We just calculate what is the change in absorbance. Let's say, for example, delta OD number 1 was 1.2 and delta OD number, OD number 1 was 1.2 and OD number 2 was 0.8. Then we simply write 0.8 minus 1.2 is equal to 0.4. We ignore the negative sign. So the concentration of the known value sample is divided by 0.4, which is the delta absorbance of the known value sample. And then this factor is used to calculate the concentration of unknown value, where again the concentration of unknown value is equal to delta OD of unknown value multiplied by the factor. Again, we are taking into account the change in absorbance of the unknown value or the patient sample. Now, friends, what is the meaning of fixed time kinetics or two-point kinetic? Now, fixed time or two-point kinetic is exactly the same as rate kinetic. There is only one particular difference. In rate reaction, we have seen in a previous video that we have to take the absorbance only in the lag phase, only in the log phase of the reaction. We cannot take the absorbance in the lag phase of the reaction. Now, let's say hypothetically, the log phase of the reaction is up for lasting up in for 120 seconds. Say, for example, this is 0 second and this is 120 seconds. So for 2 minutes, the reaction is in the log phase. Now, in case of kinetic reaction, we can take both these absorbances anywhere between 0 second to 120 second. But in case of fixed time kinetic, we cannot change these measuring points. For example, if in the pack insert, it is mentioned that delay time is 30 seconds. So delay time is the lag phase of the reaction. Then measuring point number 2 or measuring point number 1 is, say, for example, 30 seconds and measuring point number 2 is, say, for example, 90 seconds. We cannot change these two measuring points. We have to take the first absorbance at 30 seconds only and we have to take second absorbance at 90 seconds only. When we cannot change these two measuring points, this type of reaction is called as fixed time kinetic reaction. But in case of kinetic reaction, we can change these two measuring points as long as both the measuring points are in the log phase only. So instead of 30 and 90, we can take the reading at 40 and 100 seconds also. That is with kinetic reaction. But with fixed time, we cannot take the reading at 40 and 100. We have to take at 30 and 90 only. So when the measuring points are fixed, this particular type of reaction is called as fixed time kinetic reaction. This is true while estimating creatinine or urea. The reason for this is because, as seen in this particular graph, the graph is linear. But in case of certain parameters, the graph is not linear. It is curved, which is called as a parabolic graph. So when the graph is parabolic, we have to keep the two measuring points constant between the standard as well as the patient sample. Then only we will get accurate results. Friends, this is the difference between kinetic reaction and fixed time kinetic reaction. If this video has been helpful for you, and if you have any questions or if you have any kind of suggestions, please do write in the comment section. It will help us to improve our future videos. Thank you very much, friends. I will see you in the next video.